Okay, let's get started for statistics 115 again. In the last lecture, although everybody watched the video, we talked about differential gene expression and false discovery rate. So basically, after you have expression microarray, you want to see whether in different conditions, whether there are genes that are differentially expressed. By the way, I brought some old, I used Affymetrix microarray. So you can bring it home as a souvenir. They used to cost like $2,000 a piece, and now it's not. It's a worthless now. This was not a gene expression array. It's a promoter array, which covers the promoter of all the genes. Anyway, so today we're going to talk about microarray clustering. We mentioned before that after you get gene expression index, you get a list of this table where the rows represent the genes and the columns represent the samples. You can represent this as a heat map. But depending on the order of genes on this heat map, you might get very different things. And so you might want to show the genes that have similar behavior or samples that have similar behavior next to each other, which means that we need to cluster the samples or genes. And so you can see when we cluster, you can either cluster by genes, which means that the two genes over different conditions, they have similar behavior. So you cluster by row, or you can cluster by the samples, which means the different conditions, or say the different replicates in this whole experiment, they have similar expression profile across all the genes. So so the reason we want to do clustering is first we want to visualize the data better, even for simple things like differential gene expression. Very often you show people a heat map with the genes or samples clustered, you can already see a lot of interesting trend that you can use it to understand a general characteristics of the data. And you can make generalizations about gene behavior. Rather than describing as one gene, you can look at a cluster of genes. You say, okay, this cluster, say their expression go up in some condition, or it go up in 3 hours, but gradually come down in 6 and 12 hours. So you can describe the whole cluster behavior. You can also use it to classify samples, which we'll discuss in the next lecture. So when we decide to do clustering, there are two goals. As we mentioned, we want to put the samples or the genes that are closer to each other, next to each other on the, say, on the heat map. And so how do you call something as close? You know, we need a way to calculate the distance. A very intuitive way to calculate distance is by correlation. Right? So if two genes are correlated in different conditions, or two samples across all the genes are correlated, then they are very close. And so the distance you can imagine would be something like a 1 minus correlation. So it will be a number between 0 to 2, right? And so if the two genes are completely correlated, their distance will be 0. They're very close to each other, okay? Our goal for clustering, there are twofold. One is we want to maximize the between cluster distance. So if, let's just say we are trying to cluster genes, right? So the genes that across multiple conditions, they have very similar behavior. We want to put them together. We want to make sure the between cluster, so the within cluster distance are the genes in the same cluster. We want those genes to be as close to each other, but between the different clusters, we want their distance to be as far away as possible. In addition to maximizing these two, or maximizing the between cluster distance and minimizing the within cluster difference, we also want to make sure our cluster is stable. So how do we know whether the cluster is stable? You can imagine if we mass out some data, supposedly if you add just one more sample, would that make the clustering completely go crazy, right? Yeah, so if we only take 90% or 80% of the data to do the clustering, would that give us roughly similar result? Or if we introduce a little noise in the data, say for whatever gene expression, if the measure has a little error, you can add a little noise and see whether it gives you similar result. And sometimes you can change slightly on the cluster parameters and see whether roughly the genes and or samples are still clustered together. You can also try to select a subset of genes for clustering. For example, once we have an expression microarray, you have like 20,000 genes measured on that array. If you draw that heat map, each row for that gene will be tiny. But most of the genes on this microarray, as an assumption that we use for normalization, they are not going to change across all the samples. So if you only take those genes that are differentially expressed between the conditions to do clustering, you can reduce your total genes to draw on that from 20,000 to maybe only 5,000, right? Then it will be it's doable. You can also choose to draw the genes on certain pathways or things like that, but we'll talk about annotations later. Okay, so the very simple clustering that you see and we will be using a lot, and you see it in a lot of papers, is hierarchical clustering. Hierarchical clustering is a kind of a greedy approach. You just want to see which samples are closer to each other, and you always try to cluster the genes or the samples that are closest to each other. And in order to do this, we need to do a pairwise comparison of all, let's just say we are trying to cluster the genes. We want to see multiple conditions if the two genes have similar behavior. So we want to calculate all the pairwise distance. You can calculate a Pearson correlation of their gene expression, right? And so if you have like 10,000 genes, it will be 10,000 choose 2, right? All the pairwise. Then we choose the pair that have the closest to each other. We try to merge them together. Okay, so supposedly the gene 1 and 2 are the closest. This will create a new node. And you try to calculate this, and you pretend this now is a single gene. And you try to calculate the distance of this new node to all the other genes as well. And so that creates some new distance. And you compare the previous pairwise distance and this new node's distance to all the other genes. And then you pick the smallest distance again. And let's just say the second time you picked 3 and 7 as being the closest. And that creates a new node. And then you calculate this new node's distance to all the other genes and other nodes again. And then among all the distances, you pick the next closest one and you try to merge them. Okay, so in this case, a new gene is merged to a previous node, and this creates a new node, and you use this node to calculate the distance with all the other nodes. And you just greedy, add one at a time, and at the end, you will have just one node. If you do hierarchical clustering at the very end, you will cluster everything together. But most of the time, people care about looking at those smaller clusters to see the behavior within each groups. Okay, so yeah, you can see you repeatedly merge the two nodes. The node can either be a single gene, or it could be formed by a few genes to form a small cluster. You merge the two nodes that are closest to each other in terms of, say, expression correlation. And then you recalculate the distance from the newly formed node to all the other nodes. And in hierarchical cluster, the branch length from here to this place, actually the branch length is from this branch to this branch. They give you the distance between the different nodes, okay? So one thing we have to decide is linkage. When you have a new node, you try to calculate the distance to the other nodes. How do you calculate that? There are a different number of ways to do this. A very simple way is called the single linkage, which is supposedly you have one node with already 4 genes in that cluster. You have another node with 4 genes in that cluster. Single linkage means you find the 2 nodes that are the closest to each other. It's the kind of the minimum distance between the 2 clusters. And that's the single linkage. Complete linkage, which is the default for hierarchical clustering, is among the genes in the 2 clusters, what's the maximum distance between them? So that's called a complete linkage. And so it's like the furthest possible nodes in the 2 clusters. In the early days, there are also other algorithms that use average linkage, which is the pairwise. You calculate all the orange to all the red, all the pairwise, and then you calculate their average. Either one is okay. Most of the time, if you do complete linkage, it will be all right. Okay. So some brain teasers. If we have n data points, n genes over many conditions, how many internal nodes are there in the hierarchical clustering tree? So we try to merge. At the end, you have just one node, right? The one node, that's also an internal node. But every time you merge, you create an internal node. How many for a hierarchical clustering of n genes? How many internal nodes do you have? You have n-1 internal nodes, because every time you just merge, right? Imagine the situation, you just merge the first one, and every time you add a new gene to this node, another gene to this node, it's like similar, right? And how many possible ways can you draw this hierarchical clustering tree? Yeah, it's 2 to the n-1. Because at every internal node, there is a chance of drawing it this way or that way. Right? Next time you merge, you create an internal node, you can draw it this way or that way. So a good implementation on hierarchical clustering will try to make sure that even though you have a choice, they will try to, for example, in this case, make the 2 and 3 more closer to each other. Yeah, question?
So just a quick question about when you're merging nodes. So like when you merge gene 1 and gene 2, then those become a single cluster, and you measure the difference between gene 1 and the cluster of gene 1 and gene 2 and gene 7.
So for example, if we were to use single linkage, we will ask, there is a gene 1 to gene 7 distance and a gene 2 to gene 7 distance. Which one is the smallest? That will be the new distance between this cluster and the gene 7. But if you use complete linkage, it will be the maximum distance between gene 1 to gene 7 and gene 2 to gene 7.
So it's not that you like merge gene 1 and gene 2 into one cluster and then measure the distance between that and gene 7, and so you look at gene 7 versus gene 1 and then gene
right. 2. You use the members to really measure the distance. Okay. Yeah, and then the average linkage will be the average distance between gene 1 to gene 7 and gene 2 to gene 7. Okay, you don't really form a new node to create an average expression index, right? Yeah, so you can imagine, as we mentioned, at every internal node, there is a way to draw the two nodes one way or the other. And since there are n-1 internal node, there are 2 to the n-1 possibilities of drawing this. And if a hierarchical clustering algorithm is implemented well, they will make sure that things that are close to each other, like this 2 to 3, they will try to make it more similar, and like 4 to 5 to be more similar than to 6, something like that. Okay. So that's hierarchical clustering. Questions? Questions?